You ever look at a list of numbers and just know there's a secret code hidden inside? That's what we're cracking today, the hidden logic of sequences. And trust me, once you see it, you'll start finding these mathematical patterns in the most amazing and unexpected places.
So here's our game plan for today. First, we're going to warm up our pattern spotting muscles. Then, we'll dive into the two main types of sequences, the only two you'll probably ever need. After that, we'll open up the toolkit and grab the formulas that do all the heavy lifting for us, put them to the test, and then see how this all connects to the world outside the classroom.
All right, first up, let's kick things off with a little brain teaser, just to get us in the right mindset for finding the logic hidden in a string of numbers.
Okay, so you see this, 3, then 9, then 27. What do you think comes next? Yeah, you probably nailed it. We're just multiplying by 3 each time, so the next number is 81. Simple enough, right? But what if I asked you for the hundredths number in that pattern? And see, that's the real puzzle, isn't it? How do we jump from just figuring out the next number to being able to predict any number, no matter how far down the line, without having to write out all 100 steps? To do that, we need a system.
Well, it turns out most of the patterns you'll run into fall into two main categories, or flavors, if you will. And just understanding the difference between them is the secret key to unlocking all of this.
First, you've got arithmetic sequences. The best way to think about these is that they change by adding or subtracting the same number over and over. So in this example, you start at 23, you take away 4, you get 19, you take away 4 again, you get 15. You see? That minus 4 is our constant difference. It's a nice, steady, predictable change.
And the other flavor? That's geometric. Now, instead of adding or subtracting, these sequences grow or shrink by multiplying by a constant number. Here we start at 40, we multiply by a tenth, or 0.1, to get 4. We do it again to get 0.4. You can already feel how much more dramatic this kind of change is, right?
So let's just boil it down. This is the main takeaway. Arithmetic is all about a constant difference. Think steady, straight-line progress. Geometric is all about a constant ratio. That's where you get that explosive exponential growth or that rapid decay. Just being able to spot which one you're looking at is 90% of the battle.
Okay, great. We know how to spot the patterns. Now it's time to open up the toolkit and grab the powerful formulas we need to actually work with them.
This formula right here, this is the answer to that problem we had earlier. It lets you find any term, what we call the nth term, in an arithmetic sequence without doing all the tedious counting. All you need is the first term, a sub 1, that constant difference, d, and n, which is just the number of the spot in line you're looking for.
And you guessed it, there's a matching formula for geometric sequences. It looks pretty similar, but notice the big differences. We're multiplying, and we've got an exponent in there. For this one, you just need that first term, a sub 1, and that constant ratio, r. This one is built to handle that super fast growth or decay we were talking about.
Okay, now for one of the coolest, most mind-bending ideas in all of math. Imagine you have a geometric sequence that's getting smaller and smaller, and you decide to add up all of the terms forever. Your gut instinct tells you that the answer has to be infinity, right? But it's not. With this formula, you can actually get a single finite number for the sum. But, and this is a huge but, it only works if that common ratio, r, is a fraction, somewhere between -1 and 1.
All right, enough theory. We've got the concepts, we've got the tools, let's actually get our hands dirty and solve a couple of problems.
So let's go all the way back to that first pattern we looked at. 3, 9, 27. Jacob is confident the next number is 81. But Vusi, he disagrees. He says the next number is actually 57. So who's right? Or is it possible they both could be?
Now before we answer that, let's just make sure we have our process down. Anytime you face a sequence problem, it's really just a simple 3-step dance. Step 1, figure out what kind of pattern it is. Step 2, grab the right formula from your toolkit. And step 3, carefully plug in your numbers and solve.
And here's the wild answer to our puzzle. They can both be right. See, Jacob saw the most obvious pattern, the geometric one, where you just multiply by 3. But Vusi found a different, more complicated quadratic rule that also perfectly fits those first 3 numbers. And this teaches us something super important. A few numbers in a row don't mean anything until you actually state the rule that defines the pattern.
So identifying the pattern is step 1, and we see how crucial that is. But even when you know the rule, step 3, just doing the calculation, can have its own little traps.
I just love this quote from one of the sources we looked at. The instructor is in the middle of solving a problem on the board, and he just stops and says, "Hold up, I made a mistake, can anybody spot it?" It's just such a real human moment. Turns out he accidentally flipped a fraction upside down when calculating the common ratio. It's a mistake literally anyone could make. And really, that's the biggest lesson of all. Getting it wrong isn't failure, it's just part of the process of getting it right. Doing math isn't about being some perfect genius. It's about having a process, checking your work, finding your mistakes, and fixing them. That's how you build real skill. That's how you build real confidence.
Okay, so we can solve problems for a test. That's great. But what's the big picture? I mean, why should any of us care about this stuff once we leave the classroom?
Well, the reason this math is so important is because these patterns are literally everywhere. An arithmetic sequence can model how your savings grow if you add the same amount each month. A geometric sequence can describe how a population explodes, or the way a bouncing ball loses a fraction of its height with each bounce, or even how radioactive materials decay over time.
I mean, just stop and think about how universal this is. The perfect spiral of a nautilus shell, the way a tree branches out, the compound interest growing in your bank account, they all operate on the fundamental logic of sequences. It's like we found one of the core languages that the universe is written in.
So, there you have it. We started with a simple number puzzle, and we ended up with a powerful toolkit for describing how things change all around us. The real goal here is just to encourage you to keep your eyes open. The world is absolutely full of these elegant hidden rules, so the only question left is, what patterns are you going to find tomorrow?